Hello, I would like to welcome you to lecture 22 of 2FH3. We'll discuss today magnetic torques, magnetic dipoles, and applications. We cover chapter 8, pages 343 to 350. If we consider the rectangular dipole, the rectangular loop shown here, you can see there is a current flowing in this loop, and this loop is placed in an external magnetic field B. The direction of the current and the direction of the magnetic field are normal to one another, and according to Ampere's motor equation, there will be a force. This force is given by I dl cross B. So if you take the cross product between this direction and B, you get a force in this direction here on this arm. If you get the cross product between this direction and B, you get a force boiling this one downward. There are no forces on these two arms, this one and this one, because DL and B are in the same direction. So what is happening here is that you can see you have two opposite forces, F naught and minus F naught. They are opposite to one another, but they are trying actually to make the loop rotate. They're trying to create a torque. They are trying to create a torque here. So if you take a look at this loop from the side, so if you come here and take a look at the side, what you're going to be seeing is this part here. And if you assume that the plane of the loop is making, the normal of the plane of the loop is making an angle alpha with the direction B, then you can see that the torque resulting from this configuration is simply given by F multiplied by this distance. So if I fill this triangle, this is the distance I'm talking about. Okay, this is the torque really between these two forces, and this length here is nothing but F sine alpha. This length here is nothing but F sine alpha. This is the normal distance between the two forces. Is nothing but W the sine alpha. So we can simply say that the torque, the modulus of the torque, because the torque is really a vector, it has a direction as well. The modulus of the torque is equal to the modulus of the force multiplied by this length, and this length here, as we said, is W sine alpha. What we can do, we can try to find the expression for the force from Ampere's motor's equation. We know that the force is equal to I dl cross B, so we can simply write that I dl cross B. We agreed that B and dl and B are normal to one another, so this will give you I dl multiplied by B. But if you integrate for all elements along this segment or along this segment, you will see that the total magnetic field you get is equal to I L multiplied by B, because it does not really depend on the location. B is assumed to be uniform. So if you put all this together, the force, you replace the force, the modulus of the force, by IBL. This is W, this is this distance between them. Alpha is the angle between the normal of the plane of the loop and the direction of the magnetic field. Now we take LW. LW is the area of the loop, so it has a length of L, it has a width of W, so LW is the area of the loop, we call it S. And now we can put this expression, which is the torque, the modulus of the torque, into the more general expression that the torque in general is equal to M cross B. You have sine alpha here, so sine alpha is an indication of a cross product between two quantities. The first one is the magnetic field. The second one is the torque, which is assumed to be normal to the plane here containing these. It's the magnetic moment, which is assumed to be normal to the plane of this loop. So now we defined a new quantity called magnetic moment. Magnetic moment M. M for any loop is nothing but the product of the current of the loop by the area of the loop, and it's pointing normal to the loop. And the torque by definition is equal to M cross B. M cross B, and you can see it is normal to the plane of the magnetic field and the plane containing also the magnetic moment, which is normal to the loop. So the torque in our case here will be in this direction of the axis of rotation. So now from this slide we got a couple of very important things. First, the definition of the torque affecting a loop is nothing but M cross B, where M is the magnetic moment and B is the external magnetic field. Magnetic moment for a loop is nothing but the product of the current by the area of the loop, and it's pointing normal to the loop. Let's see an example here on how we can calculate magnetic moments. We have here a rectangular loop. It's carrying it has an area of 10 centimeters squared. It's carrying a current of 50 amperes. It is lies in the plane 2x plus 6y minus 3z is equal to 7. And it is in this plane such that the magnetic moment is directed away from the origin. And we'd like to calculate its magnetic moment. This statement here, the magnetic moment is directed away from the origin, is very important because the magnetic moment of a loop is by definition normal to the plane of the loop. And there are two normals to any plane, either one normal one direction, one opposite to it. So we have to determine which unit normal we should use. So this is why his essay is saying that we have to consider the one that is directed away from the origin. We start by drawing a simple diagram. So here I'm showing the x-axis, the y-axis, and the negative z-axis. This is the right-handed coordinate system. This is really the plane that we are considering. I will just try to put it in red color. This is really the plane we are considering here. This is the plane where the coil is. And you can see this plane intersects the x-axis at 7/2, y-axis at 7/6, and z-axis at minus 7/3. So this length is 7/3. Of course, we have here two unit normals. There is this unit normal pointing away from the origin, and there is this unit normal pointing towards the origin. The one pointing towards the origin, as obvious, will have negative x and negative y and positive z component, but this is not the one we are looking for. Then the unit normal we should use from the expression of the plane is 2ex plus 6ey minus 3ez, and then you divide by the modulus of this vector. We agreed that from the expression of the plane, if the plane is in the form 2x plus 6y minus 3z is equal to 7, then the normal to that plane is 2ex plus 6ey minus 3ez, and then you divide by its modulus. The numbers will cooperate with us here, so this here will give us square root of 49, which is 7. So now we know what is normal to this plane. The magnetic moment of a loop, by definition, is equal to Is multiplied by the unit normal. We know the current is given, the area is given, and now we calculated the unit normal. Then we can calculate the magnetic moment of this rectangular loop. And again, it can be rectangular, it can be square, it can be circular, and for all of them, this is the definition of the magnetic moment. So we put all these numbers together, so we can see here that this is the value of the current, this is I. The area is 10 centimeters squared, so you multiply by 10 to the minus 4 to convert it to meters squared. And then this is the unit normal. If you simplify everything and you multiply, you get 1.429 in the x direction, 4.286 in the y direction, minus 2.143 in the z direction, and this all multiplied by 10 to the minus 3. Units of the magnetic moment is ampere meter squared because it's the product of current with area. It is current with area in the direction of the unit normal to the loop that we have. Now we start to discuss something very important in magnetostatics, which is the concept of magnetic dipole. The book really does not give a derivation for the magnetic vector potential of this magnetic dipole, but I will give you a detailed explanation. I think it's very important to understand where they get the expression used in the book. The book doesn't give an explanation, but I will show you how we can derive that. So what's happening here? We have a loop of current, a circular loop. It is in the xy plane, and we would like to calculate the magnetic field at any point in space, any arbitrary point, not along the z-axis. We have seen before how to calculate for z-axis, but this is a general case. So we apply the easiest way of doing something like this, and I explained to you earlier, using magnetic vector potential simplifies things a lot. Magnetic vector potential, by definition, for any loop or for any current carrying wire, is mu naught I over 4 by I integration over that wire of dl over r. dl is the unit vector, is the length, differential length along the wire. So here it's going to be this one here, any small differential length. R is the distance from every point on the wire to the observation point. So here if I take a small element, so I'm just going to take this small element here. So this is R. This is the distance R from my element, small element on the wire, which has expression here dl, to the observation point. Now we should try now to put all the ingredients of this expression together. dl is obvious here. dl is in the phi direction, and its value is a d phi. If the radius here is a, then this length here is a d phi in the phi direction. And because we'll be integrating, when you integrate a phi, as I explained earlier, you have to write it in terms of ax and ay, because ax and ay are not variable directions, they are fixed directions. If you express, we have talked about that before, a phi is equal to minus sine phi ax plus cosine phi ay. Now, this is an arbitrary point, it has x, y, and z. We will simplify things a little bit by assuming that we rotate the coordinate systems around the z-axis, so that this point becomes in the xz plane. So it's a simple mathematical trick. It is exactly the same point, it's going to be exactly the same field. But what we do, we rotate everything around the z-axis. So now this point is actually moved into the xz plane, so it becomes here. So everything is rotated such that now this is now my observation point. It doesn't have a y component. Now if this is my observation point, then it should be clear to you that the phi direction here, the phi direction which is now normal to the xz plane, is nothing but ay. Okay, so if I made that mathematical trick, you will see how things will get simplified. So now we start. Vector r is the length r is the length pointing from an observation, from a point on the wire to the observation point, and its length is what we need here. And I have a word of warning for you that this length r is a function of phi, because here there is a certain r, while here there is a different r. So it's a function of phi, it's not independent of phi. Okay, so you cannot say here I'm integrating sine phi is going to give me 0, cosine phi will give me 0, because r is also a function of phi. So how we start? Every point here on the wire has coordinates a cosine phi ax plus a sine phi ay. This observation point is in the xz plane. We agreed that we already rotated the planes to get that. So now this one has coordinates only x, ax, and z and y, and for this one here we can calculate also the difference between them. So so here this is what we have is going to be x, ax, and y, ay. Well, there seemed to be a typo here in this slide, because this point here is not correct, because we agreed that we rotated the axes such that the observation point is in the xz plane. So if I will correct that, I will correct it as we go. So this becomes z az, okay, and the coil, of course, every point in the coil is in the xy plane. Okay, so if you subtract these two, this is what you're going to be getting. I will correct this one as well. This would be x minus a cosine phi in the x direction. This is fine. This one here, there is no y here. Of course, there is no y, so I can simply erase this y here. There is no y here, and there is one missing term. I think now things are in order. This becomes z az. Okay. Now this is a vector pointing from any point in the coil to the observation point. Now we try to get, we need the length of that vector, so we need r. So we have to take the length, so it is the square root of this square plus this square plus this square. This one will give me x squared minus 2ax cosine phi plus a squared cosine phi squared. This will give me a squared sine phi squared. A squared cosine phi squared from here will be summed with a squared sine phi squared from here will give me a squared. Here you get x squared, here you get z squared, and then there is one more term minus 2ex cosine phi. So this is really the length of the vector pointing from my element on the wire or the loop to the observation point. So now the coordinates look fine. We had a typo in this one, but we fixed it now. We can proceed. So if you assemble all these terms together, this is now r squared. I remove the square root. This is r squared. We can take x squared plus z squared as a common term, and now neglect a squared over x squared plus z squared, because we assume that we are calculating the field far from the wire and the loop is small. Then a is way smaller than x squared plus z squared. Remember, x and z are the coordinates of the observation point, which is assumed to be far of that small loop. Then a squared over x squared plus z squared is neglected. Okay, so now this is what we have. You get, if you divide by x squared plus z squared, you get 1, and then this term divided by x squared plus z squared. Now what we need in our calculations is 1 over r. We need 1. We don't need r squared. We need 1 over r. So we need r minus 1. But r minus 1 is nothing but r squared raised to power minus 1 half. So what you have to do here, you have to raise everything here to power minus 1 half. So this becomes power minus 1 half. This term here, when you raise it to power minus 1 half, we know we use the very simple expression that 1 plus x to the power minus 1 half, if x is small, is 1 minus x over 2. And this is what we did here. So you can see I erased this term here because a is way smaller than x squared plus z squared. So I assume now that the numerator is way smaller than denominator. So this is now is the term inside the bracket. It's smaller than 1. Then when I raise it to power minus 1 half, this equivalent to 1 plus this term, 1 plus this term multiplied by minus 1 half. And this is what I did here. So now this is the expression I should plug into the integrals. Now we have two things. We have to multiply, this is 1 over r, this is 1 over r. I have to multiply by the sine phi ax, and then integrate, and have to multiply it by cosine phi ay, and then integrate. Notice one thing, that if you multiply this one by sine phi, you get an odd function, and we'll be integrating over the loops. We'll be integrating from minus pi to pi, or from 0 to 2 pi. The integral of an odd function like this from 0 to 2 pi will give you 0. So this is why there is no x component. Okay, so if I take this one back and I take it back to the expression of the integral, if you remember, the integral was minus sine phi ax, and this will be divided by r. So you multiply this term here, the r that we have here, multiply this r, you multiply it by sine phi, but this gives you an odd function. The integral of this odd function will be 0. The only term that will remain is the other term, which is cosine phi ay multiplied by that term. Okay, and this is what we have here. This is why I said there is no x component, there is only y component. So we have to carry out this integral here. Of course, the integral was from minus pi to pi, but after I multiply this term by cosine phi, okay, after I multiply by cosine phi, I get cosine phi here, and then I get cosine phi squared here. Now this is an even function, so when I integrate it from minus pi to pi, I can simply integrate it from 0 to pi and then multiply by 2, and this is what I did here. This is why this 4 pi became 2. So now this is really the expression for the magnetic vector potential, but after we replace the r by its expansion, and after we ignore the x term, because x component, because it's gonna vanish. So the integral of cosine phi from 0 to pi, you can carry out this integral, of course, and so this one here will give us minus 1, and you get this one as well. The integral of cosine squared phi can be expanded in terms of cosine double the angle, and then you integrate from 0 to pi. After you do all this, this is the integral that you will get at the end. This is the value of the magnetic vector potential in the y direction. Just a reminder here, the integral of cosine will give you minus sine, and the integral of cosine will give you sine. Sine by and sine 0 will cancel, so this term will cancel. This cosine squared will give you 1/2, and then 1 plus cosine double the angle. The 1/2 will give you pi over 2, so pi will cancel with pi, and then this 2 becomes 4. So this is how we got this expression here, okay? Now this is the expression for the magnetic vector potential. It's great, we know it now as a function of x and z, but we have to write it in spherical coordinates, because this problem is more similar to spherical coordinates. So we replace x by r sine theta here. We replace z by r cosine theta. And remember, we assumed that our point is in the xz plane. So we assume that phi is equal to 0. So cosine phi here was replaced by 1. So, and replace, of course, x squared plus z squared replaced by r squared. So this is the expression that we get for A. And I mentioned to you as well that because of the assumption that the observation point is in the xz plane, then AY, the normal to that plane, is nothing but A phi. So we can replace here y by phi as shown here. So this is the expression for A phi, and the book simply put this expression without giving an explanation where it came from. So away from a small loop, this is the expression of the magnetic vector potential. It is in the phi direction because the current is in the phi direction, but it has this dependence. It decays as 1 over r squared, and it has a sine theta dependence. Now take a look at this expression. Pi a squared is the area of the loop. I by a squared is the modulus of the momentum, of the magnetic momentum. So to this expression here, if we try to draw it, if we say this is my loop, this is the magnetic momentum here, okay, and sine theta is the angle between the observation point B and the direction of the magnetic momentum. So we can put this one in a more concise form. We can say that this is M cross AR, M cross AR. And this is what you'll see in the next slide. So this magnetic loop, this magnetic small loop of current creates a magnetic vector potential given by this expression. And this is now the general expression. This is the one that we have to observe, that the magnetic vector potential resulting is mu naught over 4 pi r squared, the magnetic moment of the loop, which is equal to Is multiplied by the unit normal to the plane of the loop, cross AR. AR is the unit vector pointing from the center of the loop to the observation point. And here in our case, it does have to be that, of course, another problem, M is in the Z direction. Now, if you take the previous expression for A and try to apply its curl, we know that the B is equal to curl A, and this is why we calculate the magnetic vector potential in the first place. If you apply that, we have A as a function of r and theta. If you apply the curl in spherical coordinates, you get this nice expression for B. Now, if you compare this one and this one to the expression of the electric dipole, we talked about electric dipole when we talked about electrostatics. We agreed if you have a positive and negative charge, there is something called the electric dipole, and we said it's equal to the separation between the Q multiplied by the separation between them. If you compare the expression for the potential that we got for this dipole, scalar potential, and the electric field, you see they are almost identical to these two expressions. So now when we talk about a magnetic dipole, I want you to remember that we talk about small current loop. The magnetic dipole, because there is nothing called magnetic charge really. When we talk about magnetic dipole, we need really a small current loop. And this is the expression of the magnetic vector potential resulting from this dipole. This is the expression of the electric flux density vector resulting from this dipole. One last thing to mention about dipoles is that the magnetic field resulting from a dipole, which is really a loop here, is identical to the magnetic field resulting from a small bar magnet. They are identical. So the small bar magnet will create a field which has the same dependence, 1 over r, something over r cubed, 2 cosine theta in the AR direction plus sine theta in the phi direction. And also it will be affected by torque. If you put this loop in an external magnetic field, we know there is going to be torque, and this torque is equal to M cross B. And you should notice that this torque will cancel if M is in the same direction of B. So the torque is really trying to rotate the loop to make it align itself with the magnetic field. So it's trying to make it look like that, so that its magnetic moment in the same direction as the external field. The same thing will happen also for the case of a bar magnet, as you'll see. So if you put a small bar magnet in an external magnetic field, this bar magnet will be affected by torque. This torque is trying to make this bar magnet rotate and align itself in the same direction of the B, of the external magnetic field. And the torque here is M cross B. There is nothing called the magnetic charge, but we can talk about an equivalent magnetic charge. Qm multiplied by the unit vector, or by the small length vector L, pointing from the south pole to the north pole. Now let's see a couple of examples. We have here a circular conducting loop. It has a radius of 10 centimeter. It's in the XY plane. It carries a current of 3 amperes. It's put in an external magnetic field 3Ex plus 4Ez. We would like to find the loop's magnetic dipole moment, and the torque affecting that loop. The magnetic moment, by definition, is equal to the current multiplied by the area of the loop multiplied by the unit normal. This loop is in the XY plane, then the unit normal is AZ. The current it's carrying is equal to 3. The radius 10 centimeters, so it's 0.1, so its area is pi multiplied by 0.1 squared. If you put all this together, you will see that this loop has a magnetic moment of 0.094 AZ ampere meter squared. We agreed that the magnetic moment has units of ampere multiplied by area. Now, if you try to find the torque, you are putting it an external magnetic field, so this external magnetic field will try to make this loop rotate such that its magnetic moment will be pointing in the same direction as the magnetic field. So the torque affecting it, from the expression we studied earlier, is M cross B. We know M, we calculated M, and B is given. AZ cross AX will give you AY. AZ cross AZ will give you 0. Then the answer is 0.094 multiplied by 3, which is 0.28 AY Newton meter. Remember, the torque is a product of force by distance. Then the torque has units of Newton meter. Now let's see one more example. We have a small magnet. This magnet produces a magnetic field of minus 0.5 AZ milliwebers per meter squared. So it's 10 to the minus 3 webers per meter squared at 10, 0, and 0. So at the point 10, 0, and 0. We would like to find B at 0, 3, and 0, 3, 4, and 0, and 1, 1, and minus 1. So the trick here in this example is that the magnetic field, or a small magnet, a small bar magnet, will create the same field as a magnetic dipole. And we agreed that the magnetic dipole is nothing but a small loop. So now we'll try, we know we have one piece of information that at the point 10, 0, and 0, the magnetic field is minus 0.5 AZ. Then we try to find what is the expression for the magnetic field, the small bar magnet, using this given piece of information. So you start by drawing a simple diagram. This is a bar magnet. It can have one orientation or another. But the expression, that the important part here is that the expression of the magnetic field of this bar magnet is the same one we used for the magnetic dipole, which is really the magnetic loop, small magnetic loop. I here got rid of all the constants mu, I over 4 pi. I replaced them by a constant k. So if I know k, I know everything about the magnet. So what we're going to be doing here, we are giving we have one piece of information that at 10, 0, and 0, we are giving the magnetic field. 10, 0, and 0 is a point along the x-axis, so it's a point somewhere here, okay? So along this point, this is R. because r is measured from the origin. This is r here, and theta is the angle measured from the z-axis, so theta is equal to pi over 2. Okay, so theta is equal to pi over 2. And one other thing, a theta is pointing in direction of increase of theta, so a theta is pointing downward. So a theta here is negative az. So at this point, a theta is negative az. If you put all this together, substitute, you have a given value for b. Cosine theta at the given point is pi over 2, so this term is 0, this term is 1. A theta at this point, at the observation point, is minus az. Remember, a theta does not define a constant direction. It changes from one point to another, but at this specific point, a theta is pointing direction of increase of theta, so it's pointing downward. It's pointing in the minus az direction. We put all this information together. This is a given magnetic field at that point is equal to k over r cubed 2 cosine theta plus ar plus sine theta a phi, a theta. We know now r is equal to 10. Cosine theta is 0 because theta is equal to pi over 2. And we know that a theta is minus az. If you equate both sides, you get that k is equal to 0.5 10 to the minus 3, which is a given magnetic field multiplied by 1000. So the constant k is equal to 0.5. So the great thing about this approach is that we know exactly the expression for the magnetic flux density vector. And when sometimes they use the word magnetic field and the magnetic flux density vector in the same way. So I would be very careful when I ask you for a quantity, whether it is a magnetic field strength, it's H, or the magnetic flux density B. Now for any other point, so at the point 0, 3, and 0, this is a point along the y-axis. So if you go here and you draw, this is x, y, this is a point here, 3. So at this point, this is r. R is the distance from the origin, 3. Theta here again is equal to pi over 2. And the direction of increase of theta is minus az. So I can go to this expression, calculate the field at 3, 0, and 0, both r equal to 3, both theta equal to pi over 2, and replace a theta by minus az. Because at the observation point, a theta is pointing downward. So for the second required value, we have k is equal to 0.5, r is equal to 3, cosine theta is 0, sine theta here is equal to 1, but a theta is equal to minus az. If you put all this together, you get that your b is equal to minus 18.52 milliwebers per meter squared. So there is a 10 to the minus 3 here. Now, we are asked for one more point, 3, 4, and 0. 3, 4, and 0 is a point in the xy plane. So if this is x and this is y, it's a point somewhere here. So at this point, this is r. R here is nothing but square root of 3 squared plus 4 squared. This is theta. Theta is pi over 2. And the unit normal in direction of increase of theta again is minus az. Okay, so at this observation point, r is equal to 5 square root of 3 squared plus 4 squared. Theta is pi over 2, and the a theta is minus az. So now we can go back to the expression that we had. Both r equal to 5, cosine theta is 0 because theta is equal to pi over 2. Sine theta is 1, but a theta is minus az. So you get minus 4 milliwebers per meter squared. The last thing is a general point, 1, 1, and minus 1. And for 1, 1, and minus 1, we can calculate r. R is the square root of x squared plus y squared plus z squared is equal to square root of 3. Tan theta by definition, if you can, of course, you can draw that. This is theta here. This is theta. This is z, and this is rho. So theta, tan theta is equal to rho over z. Rho at this point is nothing but square root x squared plus y squared square root of 2. Z is minus 1. So this is the tan of the angle. Of course, it's an angle greater than pi over 2. Then the sine will be positive and the cosine will be negative. These numbers are coming from the famous triangle, which is 1 square root 2 square root of 3. Okay? So we have all the information that we need for the expression. We put r equal to square root 3, we put cosine theta equal to minus 1 over square root 3. We put sine theta square root over square root 3. So if you put everything together, k over r cubed, this is cosine theta ar, actually this is 2 cosine theta ar, it's minus 1 over square root 3, plus sine theta a theta. Of course, ar and a theta here will depend at the current point. So they are really functions of ax, ay, and az, and you can get them as functions of ax, ay, and az using the coordinate transformations we talked about earlier. If we put everything together here, the answer is minus 111 ar plus 78.6 a theta milliwebers per meter squared. So there's a 10 minus 3 here.